Good afternoon, everyone. I'm Mike Zheng from the Ohio State University. Today, I'm going to talk about our recent work, torturing databases for fun and profit. This is a joint work with my colleagues from Ohio State and HP Labs. So today, we have many important data. Some are valuable and some are priceless. So we use databases to keep our data safe. Databases are designed to provide ACID properties, which means atomicity, consistency, isolation, and durability, even under failures. So you want to know which database can protect your data all the time. I'm telling you now. Yes, this is the full list of databases that passed our testing. Everything is broken under our simulated power faults. Not a single database can survive all of the tests in our experiment. So I will put my money under my mattress. You may think I'm paranoid since power faults cannot happen nowadays because of UPS, careful design, and more money, right? Unfortunately, that's not true. Besides the Super Bowl event last year, even the experienced data center operators cannot 100% guarantee continuous power. Moreover, some other events like system crashes may also make a database stop unexpectedly. So it's important to thoroughly evaluate databases under failures and fix the potential defects. And our work helps in both testing and diagnosing the problem. Of course, we cannot cut the power off manually for millions of times. So we need simulation. And we need to be precise on what we want to simulate. That's why we define a fault model. Our model is simple. It's a clean termination of I/O string. Under this model, there exists a minimum atomic transfer unit. A fault can happen at any time. But once a fault happens, all of the on-the-fly blocks have no effect on the underlying storage media. And all of the blocks transferred before the fault are durable without any corruption. As you can imagine, this is probably the simplest scenario a database may face under power outages or system crashes. We focus on such a simple and nice model for two reasons. First, it seems unreasonable to require databases to handle arbitrary corruptions introduced in the lower layers, given that they so badly violate the API contract of the underlying storage system. Second, unless we have an extensive study on the real patterns of corruptions happened in reality, introducing severe corruptions or aggressive reordering and considering how to handle those terrible things may not be worthwhile because the simulated effect may never happen in practice. On the other hand, our clean power fault model is a clear and safe lower bound on the failure behavior. A database must be able to handle this model gracefully if we want to keep data safe under failures in the real world. So given a clearly defined fault model, how can we test databases on multiple operating systems with high fidelity? We don't want to change the thread scheduling as some previous work did because it may affect concurrent transactions. Also, we don't want to disturb the interactions among the database and the kernel components like the file system, the memory manager, the I/O scheduler, and so on. Any modification in these layers may affect database and thus affect fidelity. So how do we do that? The design choice we made is to decouple the database from our system through the iSCSI layer. iSCSI is a protocol that allows one initiator machine to access the broad device on a target machine over the network. To everything above the driver on the initiator, iSCSI is completely transparent, which makes it a perfect place for our purpose. Although we focus on databases in this work, the SCSI command level framework is actually capable of black box testing every storage layer or the whole storage stack running on top of a broad device with high fidelity. So how does our framework look like? Basically, there are three stages. First, the worker applies a workload to stress the database and generate SCSI commands. And second, the recall and replayer simulates the effect of power failures during the workload. And third, the checker checks the post-fault database. Different from undirected testing, we have carefully designed workloads to simulate, to stress different aspects of the database and to allow easy checking of ACID properties. Here's an example. In this example, we partition the database table into meta loads and workloads. There's one meta load for each transaction. For example, we have 2 threads, and each thread has 2 transactions, so there are 4 meta loads in total. Every load has an initial value so that we know the initial state of the database. Each transaction updates multiple workloads and one meta load. For example, thread 1, transaction 1 randomly selects 2 workloads and saves its transaction ID there. And then it saves the 2 workloads and the timestamp right before the commit in its meta load. Similar transactions from multiple threads are executed concurrently to fully exercise the concurrency control of the database. Oops, what's going on here? A power fault just happened during our workload. So after bringing back the power, we check the recovered table to see if there's any ACID violation. For example, we see a transaction ID in a workload, so we trace to the corresponding meta load and check the value there. Clearly, there's an atomicity violation because the meta load update in this transaction is missing. In addition, the timestamps allow us to check time and order related properties easily. And we have more workloads and ACID checking in the paper. Besides the carefully designed workloads and checking logic, we have a recall and replayer to simulate the effect of power failures during the workload. When a worker applies the workload, we intercept the generated SCSI commands in the target daemon and recall the worker's block trace, which contains a sequence of minimum atomic block transfer operations below the SCSI commands. Because the target daemon can be implemented in the user space, we can capture the trace without any kernel modification. After getting the trace, we create a post-fault disk image by selecting a fault point and replaying all of the minimum block operations before the fault point. To check a post-fault database, we use the failure image as a backing store of iSCSI and allow the file system and the database to perform self-recovery and then check the recovered table. The recall and replay systems allows us to test different fault points easily. As you can see, this is a very fine-grained and thorough testing in that we exhaust every possible power fault point under a given workload. However, the framework discussed so far is not good enough. There are too many minimum operations and thus too many potential fault points. Sometimes we may need several days to complete one exhaustive testing. We have tried sampling, but soon we found that only a few fault points trigger ACID violations, which makes sampling not effective at all. And most importantly, we don't know why those few fault points cause the trouble, and let alone how to fix the problem. In order to identify those special fault points and to understand the root cause, we need more context information. So we enhance our design by introducing a multi-layer tracer. The original trace only includes the content and the LBA of each minimum operation for replaying purpose. The enhanced tracer gathers additional context information, including the timestamp of each minimum operation, the SCSI command number of each operation, the file that each operation transfers the data to, and the system call that triggers the minimum operation. The files are correlated with the operations based on LBA, and the system calls are further correlated based on timestamp. So this combined multi-layer trace spans everything from the minimum block transfer operations to the system call level behavior and allows us to understand much more. For example, each database file usually has a well-defined functionality, such as undo or redo log. So by correlating the reblog operations with the file, we can infer the semantics of the database around the 4 time. How do we actually implement the tracer is a little time consuming to explain, so I'm not going to get into details here. With the detailed context information, we analyze the traces collected in our early experiments and try to figure out why some 4 points are so special, and if there's any pattern in the context that can be used to predict those special points. And we do discover 5 patterns based on the early traces from 2 databases. For example, the mmap pattern describes the unintended update to the memory mapped blocks. In this particular pattern, there's a region of 4 points triggering ACID violations, and after the region, there's an msync on a memory mapped database file, which implies that this operation is an intended update by the database. And before the region, there's another update to the same location. However, this update is caused by fsync on another file, so it is unintended. Such unintended update may be caused either by the kernel thread or by the file system under heavy transactions. And the underlying database file may become inconsistent until the next intended update. So the mmap pattern considers the 4 points between the 2 updates as special. And there are 4 more special patterns in the paper. After discovering the 5 special patterns, we add a fault injection policy component to determine where to inject faults. Given a worker's trace with detailed context information, we check each operation to see how many patterns it matches, and assign 1 point to the operation whenever it matches a pattern. For example, both operation number 7 and number 8 match the mmap pattern, so we assign 1 point to each of them. Similarly, we check with other patterns and assign 1 point to an operation whenever it matches a pattern. And finally, we sum out the total score for each operation and rank the operations based on their total scores. For example, the operation number 7 has the highest total score, so it is in the first rank. Injecting a power fault in the first rank operation is most likely to trigger ACID violations because the first rank matches the most special patterns. So instead of exhaustive testing, we can directly inject the power fault at a predicted most error-prone first rank operation. Besides predicting the special 4 points, another challenge is how to diagnose the problem so that we know what happened and how to fix it. The workers multilayer trace discussed earlier already gives us detailed context information around the 4 time. In addition, we add a function call tracing to disclose more semantics of the database. So now our multilayer trace covers everything from the application level semantics to the lowest level of minimum block transfer operations below SCSI commands. Similarly, when an ACID violation is found, we replay from that particular 4 point and enable the same tracing to see why the recovery didn't work. And we will show how to use the traces to diagnose a real bug case in a minute. Okay, that's all about our framework. Let's continue to see what we have found. We have evaluated 8 databases, including 4 open source ones and 4 commercial ones. We evaluated them under 4 carefully designed workloads, and on 3 file systems, and on several operating systems. Here's the result summary again. And as mentioned earlier, not a single database can survive all of the tests in our experiment. The most common error is durability violation, although durability may be violated in a different way in different databases. The last 4 columns show for each type of the ACID violation, the percentage of power faults that trigger the violation among all power faults injected exhaustively. And we can see that some violations are very difficult to trigger. For example, LightningDB violates durability under only a tiny percentage of power faults injected. But our pattern-based approach can capture this violation effectively. In fact, we didn't know anything about LightningDB before testing. But once we have observed violation, we diagnosed and understood the root cause within 1 day based on our traces. And we have included a detailed analysis in the paper. Here, let's go through a relatively simpler case, which caused atomicity violation, durability violation, and consistency violation in Tokyo cabinet. The exact failure symptoms include a transaction is partially committed, and some rows are broken, and the retrievable rows by different query methods are different. First, we are curious about why the recovery didn't work. So we apply delta debugging and compare the checkers trace when ACID violations were found with the checkers trace when no violation was found. And quickly, we find that a restore function is missing in the abnormal recovery trace. Moreover, we can see that there's a read from the database file in both traces. However, the content is slightly different. The difference in the database file suggests that some update to the file during the workload changes the recovery behavior. So we then look at the workers trace around the bug triggering 4 points. In this example, force injected among the operation number 30 to number 90 caused the trouble. So we can see that after the operation number 90, there's operation number 91 matched the content in the normal recovery trace. Moreover, we find that there's an msync on a memory mapped database file, which implies that this operation is an intended update by the database. And before the operation number 30, we find another update to the same location. And this update matches the content in the abnormal recovery trace. Moreover, we find that this update happens when calling fsync on another file, so it is unintended. Apparently, there's a gap of understanding or assumptions between the database developers and the OS implementers. And so a power fault happens after such an unintended update, but before the operation number 91 will leave the database file in an inconsistent state and thus affect the recovery. This is the root cause for this case. And by the way, the mmap pattern described earlier is extracted from this case. So now we have pinpointed the root cause, we can find solutions. And one solution is to use the failure atomic msync, which can prevent the implicit flushes of dirty blocks. And the pattern-based fault injection works well. This figure shows the reduction factor for each database, which is defined as the number of test points under the exhaustive policy divided by the number of test points under the pattern-based policy. Apparently, it's the higher the better. So for most of the databases tested, patterns reduce the required test points by more than 19 times while achieving similar coverage. As mentioned earlier, the patterns are extracted from 2 databases manually. But we can see from this figure that they are also quite helpful for testing other databases. To get a more concrete sense of reduction, we also compared the testing time. For example, patterns reduce the required testing time for SQL B from more than 2 months to less than 3 days. Apparently, this is a great improvement. To conclude, we have shown that even some well-tested databases may lose data under simulated power faults. This is a wake-up call. Traditional testing may not be enough for today's complex storage systems. Instead, we need thorough testing, which requires carefully designed workloads and intelligent fault injection techniques. And it turns out that different layers in the operating system can help us in a different way. For example, the iSCSI layers allows us to inject faults with high portability and high fidelity. And the LBA and system core allows us to capture the common behavior patterns of the applications. The patterns we extracted is far from perfect, and we believe sophisticated data mining or machine learning algorithms may help a lot here. And finally, we feel that we are in the urgent need of bridging the gaps between different parties. To see what a gap means, let's do some pop quiz here. true or false for the following statements. The first one is easy if you didn't fall asleep in the last 20 minutes. Memory mapped files may be updated without anything. The other ones are more tricky, but since we are running out of time, let me throw out the answers directly. If any of these answers surprise you, just like the first two surprised some database developers, and the last one surprised perhaps more than 99% of users, including me, then you may feel the gap between you and the other side. How can we bridge the gaps and make a database more user-friendly and make an operating system more database-friendly? It's an open question. Thank you. I'm happy to take questions now.
Great work for showing effects. Shilong from Spokeo. So one main question here is that, yes, as you pointed out, durability is not provided by default at some times. So my question would be, because previously it's already been known that not all the SQL database or not all the relational database runs at full transaction level by default. So I just want to make sure, did you actually try to use the most strict configuration for all the testing cases?
Yeah, that's a very good point. And thanks for the questions, which allow me to clarify something. And actually, in our experiments, we use the default setting, but we enhance the default setting when we are aware of there are more robust or more robust setting. So for example, in Tokyo Cabinet, by default, if you open a database file without a particular flag, then it does not guarantee the durability after commit. So when we are aware of flag requirement, we add the particular flags to enhance the durability. So yes, most of the testing are under default setting. So and we try our best to enhance the setting as a user. Thanks.
Okay, so I think things looks like all the facts here are most related to the durability, but not something related to isolation. Is that because not part of this paper or not part of the focus here?
Yeah, that's another good question. So in our workloads, we have multiple workloads, and in our workloads, we intentionally design rules to capture each type of the ACID properties. But as you may know, isolation may be is relatively difficult to check compared to other properties. So there are fewer rules in our workloads and checkers to capture isolation violations. So it's possible that some isolation violations are not detected by our checker. And it's also possible that those databases we tested are actually very good at provide isolations, and this is good enough to pass our tests. Thanks.
So we have time for one more question.
Phil Bernstein, Microsoft Research. This is terrific. I mean, I've been a party to database testing groups that have tried to do stuff like this to systematically test and found it extremely difficult. Do you have any, is the fraction of patterns that cause errors a good measure of the fraction of crashes that are likely to drive the system to an inconsistent state? Yes, it's erroneous. Yes, that's a problem. But just how often is this likely to happen? And do you give any? Is your technique give any hints as to how to answer that question?
So I'm not sure I understand the question correctly, but are you asking about the?
I run the
system.
Patterns? I run the system randomly. Over a period of 2 years, there's some large number of power failures, and some fraction of them lead to inconsistent states. Could I predict what that fraction is using your technique?
Oh, I see. Yes, when we run a workload, we need to recall the whole I/O trace of the workload, And the size of the whole trace depends on different databases. For example, some workloads may have about 40,000 of minimum operations, and the percentage of faults that can be can trigger violations for that particular database. I think maybe around between 10% to 20%. I mean, given 40,000 of different fault points, yeah.
Thanks.
All right,
Thanks.
let's thank the speaker.
And please come to my poster session tonight if you have further questions or suggestions. Thanks.